Hello, everyone. Thanks for the really nice introduction, Aarti. Hope you're enjoying the talks today. And this is the clicker. Okay. So I think some of you have seen me in the panel, so I kind of did the introduction already, but briefly, I work at Adobe. I'm a part of Gen AI and Sensei platform team, and the focus of our subgroup within Adobe is deep learning infrastructure for large-scale training and all of our content intelligence needs. We closely collaborate with research partners at Adobe as well as various product teams. A quick raise of hands, like how many have either trained deep learning models or like worked with colleagues who've trained deep learning models? Okay. And how many have you used um, different tools in the past 2 to 3 years? Like, have you like moved on to new tools, or is your tech stack constant? How many have you moved on? How many have you considered buy versus build decisions? Okay. So it looks like it's very common problem, right? So that's one of the main focuses of my talk. Like, how do you build a platform when everything is moving, right? When each layer that you're building on is getting disrupted, right? But there's clearly a need for a platform. Otherwise, we can't move as fast as we would want to. So here is our brief agenda for today. First of all, setting the stage, what do I mean by the complexity of building a machine learning platform, as well as the velocity that we're seeing in various layers of the platform. And some ideas that I pick from systems thinking, which helps me make decisions in terms of how to be agile when building a platform. We know that our environments change, our capabilities adapt, evolve, and our requirements change. So how do we build the systems in a way that we're agile? And some of the ideas that I like from systems thinking approaches. And I'll make an effort to put all of the different layers of ML stack in one diagram to, I find it helpful to put that diagram whenever we're making big decisions to see, what are the different layers and how are they all interconnected, because one decision might have a very, very different impact on another layer because there's a lot of overlap and there are dynamic dependencies and so on. And then finally, some decision framework that I take when making these decisions. So to begin with the complexities, I think most of us have heard of foundational models by now and how awesome they are. And one of the things I want to point out here is that in context learning, right? Not too long ago, we were building models for a very specific problem, right? Like one of the first models that I was working at Adobe was like detecting text in an image, right, for trademark issues, and we trained that model in a completely supervised way, right? Like we've collected large amounts of data and we've hand labeled it and trained a model, right? And fast forward now, like a lot of the capabilities that we've built in the past few years, now they're actually pretty doable using large language models and large vision models. One example here is this is a snippet from GPT-3 paper, where you see the GPT-3 model was never trained on translation task per se. It was basically trained to predict next word. It has nothing to do with French or English translation, right? But it does really well in, zero-shot learning might not be that well, but few-shot learning and in-context learning. So the idea of in-context learning is the models have sufficient capacity and you can prompt it at inference time on what is your task and give it some examples on how to use this on top of the foundational knowledge that it has. So in a way, I like this. I heard this from one of the talks from Christopher Potts, the linguistic professor. He says that foundational models are like this newfound aliens, right? We just haven't figured out how to talk to them. We're just learning through prompt engineering and so on. Like they already have a lot of knowledge embedded in them that, and we're just like scratching the surface of how to communicate with them to get answers that we want, right? So that's one on one hand in terms of evolving capabilities that we're seeing in research. And the size of models, when I first saw like billions of parameters, I thought it was a typo or something. Like we were like we were trying to like fit in like a few million parameters models on device, and it just heats up my phone. And phone is like unusable, right? Like, and now fast forward a couple of years, a few months, and now we're into like a billion parameter models. I wouldn't have guessed this like 2 years, like a few years back. Now we are here, like billion, hundreds of billions of parameters is a norm. So it just boggles my mind like how many various layers of ML stack do not have this assumption, right? Like a lot of things that we've built break at the scale. So how do we evolve? And this is another example I really like. Like, I think we're at a stage in a golden era in a way in machine learning where we don't have great benchmarks. Like every other benchmark is beating, is surpassing human performance left and right. Like for example, MNIST, it took like a good decade, more than a decade, since its data set was created for any machine learning model to surpass human performance. And then came ImageNet. As you can see, ImageNet probably took like 5 years, a little more than 5 years for human performance, for model to beat human performance. And fast forward Glue, right? When Glue came out, I remember like, everybody thinking like, oh wow, this is a very hard task, very hard data set. And boom, in less than a year or so, like we have models which beat human performance. So I think what I'm trying to say in this picture is like the rate at which we are disrupting ourselves is quite astonishing, and which basically means we have to evolve whatever plans we've had for our, for our systems and continue evolve. So apart from the advancement itself, there are also other dynamic environment factors which affect, change in our plans. Say, I'm sure like all of us have like 3 months plans, 6 months plans, and so on, right? Like, and one of the things which stands out, at least in our team, is like there was this GPU scarcity, right, during the pandemic, and GPUs were expensive as well as they were like hard to get by. What does that mean in terms of infrastructure? Like, do you have some critical training to do, but GPUs are not available, sorry, right, on cloud. So now do we want to completely rely on on-demand infrastructure, or do you want to, also have some, multi-year contracts and so on? And the macroeconomics, as we all are aware, like, cost is a big, it's always very important, but even more so now. How do we make the full use of our budgets and so on? And open ecosystem. This is one of the things coming from open source world. I find like, ML world is like really cool, right? Like there's so much happening in open source ecosystem. So what that means for companies is that it's not just the custom models and custom, the IP within the company, but it's also important to leverage the open ecosystem and build on top of it. And also higher level libraries, not just the core frameworks like PyTorch, TensorFlow, but you also see a lot of higher level libraries, for example, Hugging Face diffuser library, right? Like it's a very nice wrapper and one-stop shop for you to like try out various diffusion architectures and so on. And finally, but not the least, the ML tooling ecosystem is like exploding, right? Like there are like so many awesome tools that you could be leveraging. For example, Snorkel. Where so there's always this question of, okay, we have this capability but not this. Do we want to invest in building it for our team, or do we want to buy, right? And there are lots of nuances in those decisions, and it's not a decision which can be made in silos. It also depends on all of the dynamic environments that you see here. So the complexity comes from the interdependencies between all of these components and how they have dynamic relations between them. And also the offerings that, the third-party vendor offerings that you see and machine learning capabilities that you see out there, there is a lot of overlap as well, right? So it's not, some of the offerings are like end-to-end, and some of the offerings are very modular. And at least in our experience, there's no one solution just works out of the box, right? There's always some unique need that your team has and your environment and assumes, and you need to have a way to extend them. So given that context of the complexity, some ideas from systems thinking that I like is one of interconnectedness, right? So in large companies especially, we tend to have like teams focusing on one individual problems. Often it's actually very important to think of the entire system as an interconnected system, right? And establishing the relations between them. So first, I think it's important to acknowledge that it's all interconnected and then synthesize it. So there's a difference between just analyzing and synthesizing. Synthesizing also includes establishing the relationships between them and how a change affects one component. And I like this idea also. So the idea here is about feedback loops. So in this diagram, I'm basically showing 3 components, C1, C2, C3. Whereas the C1 component has a balancing feedback loop on C2, which means, if C1 component sees a growth, this C2 component kind of balances it, right? So they work nicely in a self-balancing way. But you could also see some of the, so one example I can think of in balancing loops is on-demand deep learning infrastructure, right? And building an orchestration in that infrastructure. So as more people start using these on-demand instances, our C2, which is the orchestration component, basically, efficiently releases the nodes into the pool so that, there's a nice balancing feedback loop. More people can use the on-demand instances, but we have systems in place to release it back to maintain the balance. On contrast, there can also be like few components which have a reinforcing kind of feedback loop, where a good adoption of one component in the stack could actually inversely affect adoption of other part of the stack. And we see this often, and it's important to, that's why it's important to establish how your feedback loops work in between components. And finally, the property of emergence, the value of each component versus the value of the system as a whole, right? When you combine various components, oftentimes you have an emergent property, which is not possible just by summing the components. So the sum is more than just the value from each component. So just taking those ideas and synthesizing synthesizing the ML stack now. So at a very base layer for deep learning, you want compute and data, right? That's like the bread and butter. You need GPUs or TPUs, and you want data. On top of it, oftentimes you would need some orchestration layer. For example, for compute, you might need a Kubernetes layer, which is able to schedule the parts, like bring up instances, shut down instances based on the need. And similarly for data orchestration, you need some orchestration layer which brings in your data, like data into GPU memory. On top of that, you would often need ML capabilities for experimentation and tracking. So one big difference between traditional software engineering and ML is the experimentation nature, right? Like it's given from the day one that you'll throw out a lot of experiments that you're running, which is a part of the job, right? You have to run experiments to see what works, what doesn't, and that requires certain capabilities in the platform to be able to experiment quickly and make decisions based on what you see. On top of that, we have ML core frameworks like PyTorch, PyTorch Lightning, and TensorFlow JAX, and so on. And even these are evolving. When we started like a few years back, at that time, like TensorFlow was the main thing. Now it's PyTorch, and it evolves based on the usage. On top of this, as I mentioned earlier, there are domain-specific frameworks emerging. Some frameworks are really good for transformers, for example, and some frameworks are really good for generative adversarial networks. And on top of it is models and augmented datasets. And models could be the custom models that your team is building. It could also be, open source models. For example, there are various language models, open source, like TFI, FLAN, and so on. And there's also open APIs, like you could be using APIs from OpenAI or, other similar offerings as well. And this is one of the layers I find interesting, which I see this getting added recently, where to my previous point that, think of using a large foundational model as talking to an alien. Like we're continuously figuring out how to best talk to these large foundational models and fine tune it for our needs. So there's also many frameworks coming up like GPT Index and LangChain and so on, which helps us get more value out of these large foundational models. And as these all of these various layers sees disruption, we're also seeing that there's a clear need for us to be able to quickly demo this, right? Quickly demo what does a new experience look like for our users using these capabilities. And for instance, OpenAI has released Instruct GPT like many months ago. And then it basically built a really nice engineering feat on top of Instruct GPT called Chat GPT. And I don't know how many of us have heard of Instruct GPT, but just due to the fact that this has been made available for like so many of us, it has just picked up, right? So it's very important to have those nice demos where you can showcase these features, capabilities, and have those feedback loops set up. So if you think of it like as we go up in this stack, I think we can realize better velocity. And it's not necessary for all teams to reinvent the wheel from the base layer, right? It depends on what is the size of your team. Even if you have a 2-person ML team, I think the stack still makes sense. It's just that I would recommend you start from higher level unless there is a reason, right? But on the other hand, there's more flexibility as you go down the stack here. You might want to create a new CUDA kernel, which improves the distributed training performance. The only way to do that is to have flexibility right down till the raw compute and data layer. So there's a trade-off where you want to invest. I think that depends on what are your goals and the skill sets and the sizes of the teams. As I mentioned, so there are various environmental factors here. I think we've already covered. So one of the things I want to touch upon here is that although those layers look nicely isolated, they're not. there's often a blurry boundary. So that's one thing we need to watch out for. So finally, decision framework. So how do we make decisions in this complex environment? So there is this is first thing which comes up in discussions, right? When you're making buy and burst decision, okay, what is the cost of development if you want to do it in-house? But the discussion should not end there because that's just one piece of the puzzle. The other part's cost of operations. Oftentimes, cost of operations is non-trivial, and it depends on multiple facets again. Is the service self-managed or is it a managed SaaS offering? What are the scaling properties? As is the cost depend on how we scale? Okay, if everybody likes this offering, if everybody starts using, do we pay like astronomical money? What are the scaling properties? And what are the knobs if you want to control the cost, right? Does it come at the cost of some usability or some scale? What are the knobs? So that and extensibility, as I've said, like oftentimes, like our requirements change based on the capabilities. So it is very, very, very important, no matter what tool you pick, to make sure there is some plan for extensibility, right? We don't want to be completely rethinking that stack if there's one new requirement and there's no way to extend it. And also impact on interconnected components. You might be making a decision on, for example, experiment tracking tooling. How does that decision impact your orchestration layer, for example, right? You'd be surprised how often there is some interconnectedness and they don't really work well together. And the skill sets in the team. And also, some tools are more stickier than others, by which I mean, once you start adopting those tools, it's very hard to migrate out. So you also need to consider cost of migration. Also, with all the requirements on compute and data, the cloud expense transparency is very important no matter which tool we pick. And finally, sometimes it's possible that you might say that, you know, a bag of alternatives is better than picking one. So that's also an option. So with that, I will want to close saying that change is the only constant, and I think like the only way to succeed in this ecosystem is being agile and adopting pieces from where it makes sense. Thank you.